We have Mr. Mark Pitchford, Technical Specialist, LDRA UK.
Hello, I'm here today to talk to you about the impact of medical device connectivity on certification. Here's an outline of what we'll cover. First, I'll start with IEC 62304 and functional safety. Then I'll talk about classification with IEC 62304, and then move on to the software security and domain separation. We'll then consider that domain separation in the particular context of inter-domain communication. Finally, we'll look at conclusions and summarize the presentation. So first then, let's start with IEC 62304 and functional safety. Well, what is functional safety? Well, who better to define that than the IEC? And the IEC 61508 standard was a predecessor to many of the functional safety standards in use today. According to them, functional safety seeks to reduce the level of risk in a device or system. It identifies potentially dangerous conditions that could result in harm and automatically enables corrective actions. It's part of the overall safety of a system or device that depends on automatic safeguards, and it relies on active systems that can respond to a potentially dangerous situation. This description is equally applicable across the safety critical sectors, including aircraft, railways, cars, manufacturing, and of course, medical devices. The avionics industry is strictly regulated by a number of certification standards, including DIR 178 for software, which was first published in 1992. Although it's referred to generally as a process standard, it does have functional safety as its core. IEC 61508 was published in the late 1990s and owed much to DIR 178. It's a generic standard for electric and electronic systems. It, in turn, has been adapted to specific domains, including railways, automotive, and, of interest to us, medical devices. Much of my discussion today centres on IEC 62304-2006 Amendment 1, but actually we really shouldn't be interested in this by now. We are, because the development process for the new standard failed, and so the draft edition 2 has been deleted. There's an awful lot of speculation online about why that was, and I've given you some links here so you can follow that up if you like, but a lot of it seems to point the finger at problems with expanded scope. Whatever, for now, IEC 62304-2006 Amendment 1 is still valid and still the one we're interested in. So let's look a little further at that standard. One of the key features of IEC 62304 is the classification mechanism. Here's how it used to work before Amendment 1. Let's look at that with an example. Suppose a medical device is designed for use in a hospital that is electronically controlled. A GUI uses embedded software to record and display data. A very unlikely event is that a fault in the logger could lead to a dangerous incorrect prescription. Under IEC 62304-2006, that would make it a Class C software because nothing about the probability is taken into account. So no matter how improbable the event, allocation of classification is still the same. So in our case, we would have a Class C despite this being a highly improbable event. The new definitions of class are far more wordy, but the key change is highlighted. And actually the key word is risk. It's the introduction of the term risk into the definition that makes the difference. As you can see, the software safety class assigned is now dependent on risk and not merely severity. So under the Amendment 1, our device, our logging system, is now categorized as Class A, not Class C. That, of course, is very encouraging for developers. And the reason that's encouraging for developers is because there is a substantial difference in overhead between Class A and Class C software development. So although all of these phases are similar in either case, the amount of detailed activity associated with each of them varies according to class. Any medical device software will involve verification, integration, and system testing, but the depth to which each of those activities is performed depends on that classification. Here's an example. This is subclass 542 of the standard, and it states that the manufacturer shall document a design with enough detail to correctly implement each software unit. But as you can see here, that recommendation or that requirement for that detail is only relevant to Class C. So there's an incentive to minimize the class level of any software you're working with this standard. To explain further how that influences things, let me talk you through some definitions lifted from the standard itself. These are ordered differently depending on where you look in the standard, so I'll try to bring some clarity to them. The software system can be a subsystem of a medical device, or a medical device in its own right, which then becomes a software medical device. In turn, a software system is an integrated collection of software items. The lowest level software item that is not further decomposed for the purposes of testing or software configuration is the software unit. So a software unit is the lowest level software item. All levels of composition from the software system to each software unit can be called a software item. So to summarize that, a software system is composed of one or more software items, and each software item is composed of one or more software units or decomposable software items. The actual definition of what constitutes a software item or a software unit is in the hands of the developer. So it's up to the development team or the development organization to define this level of granularity. Here's an extract from the red-line version of the standard, and it shows what changed in the 2015 amendment. The classification of the item rather than the system is important because previously an entire software system had to be classified at the same level. After Amendment 1, so from 2015 onwards, that stopped being the case. Each classification of each software item requires justification, but if that justification is possible, then this is a path that presents itself and allows a significant reduction in software development overhead. As we've seen, IEC 62304 is primarily concerned with functional safety. Connectivity changes things a great deal because it opens up the system to malicious attack. In the following few slides, I make several references to an article in the Heart Rhythm Journal, which I'll start by acknowledging, and there's a link to it here. These references illustrate the benefits of connected medical devices far better than I can, and indeed the benefits are significant. We are in an era where medical care professionals can become aware of issues with a patient's heart before the patients themselves is aware of anything being wrong at all. So what's the problem with that? Well, to answer that question, it's helpful to consider what constitutes an attack surface for a connected device or system. So an attack surface consists of all paths for data commands into and out of the application, the code that protects those paths, all valuable data, and the code that protects those data. And these elements combine to define the application attack surface. Now, in the example of the CIED from our example earlier, the analysis of an attack surface with all its contributory factors facilitates the analysis of attack scenarios. Referenced in the same article in the journal, here are a few examples of attack mechanisms. The article lists many more. It may be obvious, but it's important to note that none of these vulnerabilities exists in a traditional, isolated, static, fixed function, device-specific implementation. Of course, then all the benefits of connectivity are lost. So what we ideally want is the best of both worlds. And actually, should we worry about these attacks? Because they're very rare, so why should we bother? To start and answer that question, let's talk about Barnaby Jack. He was a world-famous, prolific hacker who dedicated his life to making connected embedded devices safer. He initially rose to prominence by demonstrating an ATM attack, but then turned his attention to medical devices. He demonstrated how a Medtronic insulin pump could be compromised before focusing on CIEDs. And tragically, he died before he was due to demonstrate the outcome of that work, but he assured people beforehand that he could kill a man from 30 feet away by attacking an implanted heart device. Although the likes of Mr. Jack did a great deal to advance the cause of cybersecurity, brilliant people of his kind have led to an unfortunate misconception for many. Unlike Barnaby Jack's examples, there might not be any particular reason behind an attack. Most hackers are like car thieves trying car doors. They're not too fussy about what they access. And what's more, to start your hacking career, you need almost no expertise at all. Tools like Kali Linux are open source, easy to use, and supported by YouTube videos. So you download them, install them, and off you go. You're a hacker. Hacking is also indiscriminate. It doesn't matter that whether your system is one you think people will hack or not. Everybody is a target. And that's because attacks tend to be automated, and traditional scanners aren't effective here. Why do people do this? Well, they do it because it's profitable. This is a database of zero-day exploits, which are available for reselling, and there's a profit to be made by selling these exploits to the unscrupulous. So it's wise to protect against these hacks, even if they're rare at the moment. You don't know when you're next going to be vulnerable to an attack. As we saw earlier, one of the key changes to IEC 62304 Amendment 1 was to allow software items of different classifications to be separated in software. One approach to defending core pacemaker functionality is to leverage the virtualization technologies in multi-core processors such as Intel's VTX and ARM's virtualization extensions. The cloud-facing virtual machine in this example might be a general-purpose operating system, or it might be vulnerable to attack from the would-be hackers, whatever it is. But it's important that the hackers cannot gain access to the heart-facing subject, perhaps an RTOS or bare metal application, even if the cloud-facing subject is compromised. To that end, the communication between the two virtual machines is tightly controlled. So we've got two domains, each of differing levels of criticality where communication between them is required. That represents a potential attack surface. What should we worry about? Well, for starters, the hypervisor provides access to both virtual machines. So what if that's compromised? How secure is the inter-process communication, the communication between these two virtual machines? And what about data endpoint? We've already seen that this is part of a wider system. Could rogue data be injected into that system? Oh, just a minute. We're talking here about domain separation and partitioning. We were talking about separation of things before, weren't we? We were talking about class decomposition. Now, for a simple isolated system, this approach always makes sense because it reduces the development overhead associated with functional safety. But communication between items of different classes represents a similar security conundrum to that we've just seen between the basic pacemaker and its connected systems. Communication between items of different classes must be defended to defend critical items from attack from less critical items. So in other words, if it's easy to access a less critical item and then it's easy to attack a more critical item from it, you've got a potential vulnerability. Failure to protect against that implies an effective reduction in the resilience of the system as a whole. An effective compromise will need items to be of sufficient modularity for communication between those items of different classes to be effectively controlled. The optimal granularity of the architecture will account for both that and the desire to limit the functional safety test overhead associated with the more demanding classes. In the interests of time, our example will focus on inter-domain communications. Founded in response to the Morris Internet worm threat in 1988, CERT regularly partners with government, industry, law enforcement, and academia to develop advanced methods and technologies to counter large-scale, sophisticated cyber threats. We'll focus here on the relevant points they make in their top 10 plus bonuses secure coding practices. The first advice they give is to validate inputs. The slide shows how data flow analysis can be used to understand exactly where and how data is used. In this case, untrusted data from outside sources is of particular interest. In the case of our hypervisor-based system, inputs to each software VM require validation in this way. Just because our two VMs are part of the same system does not detract from that requirement. That same requirement will also apply to communication between software items in a system that is to be developed in accordance with class decomposition. It is important to limit complexity. The higher the complexity, the harder it will be to understand, maintain, and test, and as a result, vulnerabilities might remain in the code. Numerous metrics can be measured, such as the number of lines of code or the fan-in, fan-out, but probably the most useful metrics are the Mccabe cyclomatic complexity metrics. This is the 7-zip software, and as can be seen in the function getOptimum, has a cyclomatic complexity of 98. This is how it's represented in a flow diagram. And here is a close-up of a small portion of that diagram. As you can see, there's an awful lot of node, an awful lot of complication there, and you really don't want to have to try and test, understand, or maintain that code. 40 years ago, in their paper, The Protection of Information in Computer Systems, Salzer and Schroeder established a principle that every program and every user of the system should operate using the least set of privileges necessary to complete a job. This invoked the principle of least privilege as was applied to personnel management in the US Army some years previously. This principle dovetails well with the decomposition of classes, provided the communication between those classes is properly managed. Most systems don't work independently. They usually pass data to some sort of data interface. So we need to make sure that data passed is sanitized, because usually the system generating the data has far more contextual information about that data than its recipient. So by sanitizing the data before it leaves our system, we can be more certain that the data has not been modified maliciously than by treating the problem as an independent input data issue. Here, for example, is a SQL injection example. If the data here isn't sanitized, input data can be manipulated such that the user ID is always interpreted as true. Again, our other systems can easily imply other items or other domains, so the separation element is important once again. Thorough defensive coding is important. For example, when calling a function to allocate memory, making sure that the memory has actually been allocated is vital. Whenever reading the memory, again, making sure that the memory is allocated is important, and ensuring that the exception and error handling associated with any failure to allocate or read that memory is handled correctly. A multiple level approach to security makes a great deal of sense, so that if the bad guys get past the first line of defense, there are others in waiting. In our example, we are advocating combining domain separation with secure coding practices, but that's just one example of many that could be applied. Once code has been tested against the requirement, it is then good to perform robustness testing. Here's how a tool can automatically generate huge numbers of test cases trying all combinations of values such as minimum, maximum, boundary values, null for pointers, etc. and so on to check that the code is robust. That automated approach brings an element of independence, given that test values are being created without user intervention. On a similar basis, many companies employ hackers who perform penetration tests to try and see if they can find any vulnerabilities in a completed system. Finally, it is recommended to develop or apply a secure coding standard. The illustration shows how adherence to a MISRA coding standard can be checked through static analysis. Some developers may prefer to use cert coding standards in this context, and they too can be accommodated. So what have we learned from our presentation today? IEC 62304 dictates objectives relating to functional safety. And what's more, it looks set to be in some place for some time yet, with the second edition having been cancelled. The standard implicitly includes safety issues resulting from security breaches. The class decomposition approach it introduces helps limit V&V overhead, and domain separation aids security. And secure coding measures applied to communications between those domains on the software items will help to maintain integrity. Well, that concludes what I have to say today. I hope it's been of interest to you. If